Hello students, welcome back to our channel Schematics tutorial. In today's video, we are going to discuss real analysis unit 1 sequences topic. This is unit 1 sequences. So in real analysis our first unit is sequences. Let us see what is a sequence first. So I'll explain you clearly with an example, but before that let us see the definition of this. General definition is a function. Suppose a function is mapping from, yes, let it be S, maps from z plus to r is called as a z plus to r is called sequence, is called as sequence. It is denoted by sequence Sn. So we can denote this sequence in flower brackets or angular brackets. Angular brackets. So I'll take an example to explain clearly. Let sequence Sn equal to, I'm taking here a function 2n plus 1 and n takes the values n equal to 1, 2, 3. You can take up to many values your wish, so on. So for n equal to 1, then s1 equal to, and substitute in place of n 1. So 2 into 1 plus 1 equal to 2 into 1. So 2 plus 1 is 3. Next n equal to 2. Then s2 equal to 2 into 2 plus 1 equal to 2 to the 4 plus 1 5, n equal to 3. Then s3 equal to 2 into 3 plus 1. So you are getting 6 plus 1 is 7. So up to we are getting here many terms. This is called as the first term, second term, third term, n terms. For nth term you are getting 2n plus 1. How the values are? The values are like Sn equal to 3, 5, 7. For n equal to 1, 3 you are getting, n equal to 2, 5. N equal to 3, 7. Up to so on. If I am taking the nth term, then I'll get 2n plus 1. Now this forms a sequence. So the numbers are in ordered format. So this is called as a sequence. Suppose, next we'll see the constant sequence definition. Constant sequence. So if a sequence you are getting the same value in all the sequence, in all the terms of the sequence, then the sequence is called as a constant sequence. For example, if Sn equal to, sequence Sn equal to, I have given a formula minus 1, sorry, 1 whole power 1, sorry, 1 whole power n I have given. Then for n equal to 1, what will get? S1 equal to 1 power 1 equal to 1. So n equal to 2. Then S2 equal to 1 whole power 2 equal to 1. N equal to 3. S3 also you'll get the same value. If you proceed this, so for n value also you are getting n equal to 3 also you'll get 1. If you proceed this till n terms, you are going to get Sn equal to 1 whole power n. 1 power anything is 1. If you take 1 power 1 lakh, 2 lakhs or millions, trillions also, you'll get the value as 1. So the value here in the sequence is only 1. 1 means a constant. So in each and every term, you are getting the constant value as 1. So now this sequence is called as a constant sequence. The same value is repeating in each and every term, then you are going to get constant sequence. Now let us see a lower bound. Lower bound and upper bound will see similarly simultaneously. Lower bound and upper bound. So the condition for lower bound is sequence Sn greater than or equal to k1. Let k1 where k1 is lower bound and k1 belongs to R, where k1 is lower bound. Here the condition for upper bound is Sn less than or equal to k2, where k2 is upper bound here. So just now we have seen an example. In this example I'll explain what is a lower bound and what is an upper bound clearly. Come, lower bound we'll see first. So here in sequences we have n equal to 1, 2, 3. For n equal to 1, 2, 3, you have got the values as 3, 5, 7. Suppose you take till here only, you leave it off remaining term. Now, so the least value of the sequence, is what here? 3. So now this will be your lower bound. So 3 is the lower bound, let us assume now. Now here k1 is the lower bound we have taken here. So now k1 value is 3. Substitute here, but Sn is holding 3, 5, 6. Sn, sequence Sn is 3, 5, 7. Sorry, 3, 5, 7. Let us check this condition. So Sn value is, first value is 3. So 3 greater than or equal to k1. K1 is 3. So this is satisfied because here the equality condition is satisfied. Next, sequence value is 5. 5 greater than or equal to k1 value is still constant 3 only. So this condition is also satisfied because 5 is always greater than 3. Next we have 7. So 7 greater than or equal to 3? Yes, 7 is always greater than 3. So this condition is satisfied. Therefore, now k1 is lower bound. Now the sequence Sn is said to be bounded below, bounded below, bounded below, because the sequence Sn is having lower bound. If the condition is satisfied, we call the sequence Sn as bounded below. If this condition fails, if it fails, then we call the sequence as unbounded below, unbounded below. If sequence Sn greater than or equal to k is not, this condition fails, then we call the sequence Sn as unbounded below. Similarly, come to the upper bound. Sn less than or equal to k we have taken, k2 we have taken. Here, the highest value of the sequence is k2, I mean low upper bound. Highest value of the sequence is upper bound. Now k2 is holding what? K2 is holding 7, and always we now we have the sequence as 3 values, 3, 5, 7. So for 3, Sn equal to 3, if we substitute here, 3 less than or equal to k value is 7. So 7 is always greater than 3, so this condition is satisfied. Next, Sn equal to 5, 5 less than or equal to 7, yes, this is also satisfied. Next, 7 less than or equal to 7, 7 is equal to 7, so this condition is also satisfied. So all these values are satisfied, then we call the sequence Sn as bounded above, bounded above. So upper bound is also called as bounded above, and if this condition fails, we call the sequence Sn as unbounded above, unbounded above. Next we'll see the bounded definition. So if a sequence Sn has lower bound and upper bound, then we call the sequence Sn as bounded. So here we have a condition k1 less than or equal to Sn less than or equal to k2, where k1 is lower bound and k2 is upper bound. If this condition is satisfied, then we call that the sequence Sn as bounded sequence. So same example we'll take here also. So we have got here Sn equal to, sequence Sn equal to 3, 5, 7, and here the lower bound is 3 and upper bound is 7. So lower bound is 3, upper bound is 7. That means k1 equal to 3 and k2 equal to 7. So we'll check whether this condition is satisfied or not. 3 less than or equal to Sn less than or equal to 7. Now Sn equal to 3 implies, so 3 less than or equal to 3 less than or equal to 7. So 3 is equal to 3, yes, this condition is satisfied. And 3 less than or equal to 7, yes, 7 is greater, so this condition is satisfied. Now next value we are having Sn equal to 5 implies 3 less than or equal to 5 less than or equal to 7. So 3 is less than 5, yes, 5 is greater here, and 5 less than or equal to 7, yes, 5 is less than 7, means 7 is greater, so this condition is also satisfied. Now Sn equal to the last value 7. So 3 less than or equal to 7 less than or equal to 7. Here 3 is less than 7. Yes, this condition is satisfied. Now 7 less than 7. Yes, this condition is also satisfied. Overall, the whole condition is satisfied. 3 less than or equal to Sn less than or equal to 7. That means k1 less than or equal to Sn less than or equal to k2. This condition is satisfied. Hence, sequence Sn is a bounded sequence. Bounded sequence. If this condition, you may get doubt, what if one condition fails? Suppose k1 less than or equal to Sn not equal to k2, means then we call the sequence as what? If Sn less than or equal to k2, then we call that the sequence as upper bound here. If this condition fails, what I told you, unbounded above, unbounded above. So as this condition is failed, lower bound exists but upper bound does not exist, then we call the whole sequence as unbounded sequence. Now Sn is unbounded. Similarly, if k1 is not equal to Sn less than or equal to k2, I mean lower bound fails, then we call that the sequence as unbounded below, and also as upper bound exists, we call that the sequence as unbounded sequence. So overall you can say if one condition failed also, you can say that the sequence is unbounded. So this is about boundedness of a sequence. Next we'll see oscillating sequence. Oscillation. What is an oscillation? Where do you see this oscillation? Oscillation you can see in a simple pendulum. How does the pendulum clock works? Here the pendulum point will be there. It goes left and then it comes to the same direction. Again the direction is changed. It goes to the right. So the simple pendulum clock rotates left side and then right side. Here only two directions will be there. Two directions. So here also after that, after two direction, once it goes to the left, left, again right. So the two directions it repeats the constantly. So here also a sequence is said to be oscillating if the values are repeating simultaneously. Two different values, lower bound and upper bound, are repeating simultaneously. For example, if you take a sequence Sn as -1 whole power n, and n takes the value for all n belongs to z plus. So here n z plus means set of all positive integer for n equal to 1. So sequence S1 equal to -1 whole power 1. So you will get -1. And for n equal to 2, you will get S2 equal to -1 whole square equal to -1 into -1 is positive 1. For n equal to 3, so S2 equal to -1 whole power 3. So -1. N equal to 4. S4, sorry, here 3. S4 equal to -1 whole power 4. -1 into 4 times, so you are going to get a positive value. So up to n values you can repeat the same. So now how we are getting the values in a sequence? Therefore sequence Sn equal to, what is the first value you got? -1. Next 1. After that again -1, positive 1. So the 1 and -1 values are repeating again and again. So this sequence is called as a oscillating sequence, because here -1 can be the lower bound and this will be the upper bound. Same lower bound and upper bound are repeating again and again. So this called as a oscillating sequence.